Hello, Kingsport. Can you all see and hear us okay?
We can.
All right. Thank you, Debbie.
Uh-huh.
So the first thing tonight is we've got this class survey. Where we need information from you folks. Remember, we got this capstone project at the end of the semester. We're using the Minitab and all that. We were going to collect information from you folks, from the students to get the data for that. All right. So the first thing is this class survey is in DQL, and you need to complete it before Friday, March 8th at 5 p.m. So here's where it is, all right? So I'm in DQL here, and I put this little news item up that shows up now. So this survey is for all the Math 1530 students, not just mine. I mean, we're talking across the whole university. The survey is anonymous. Your response will not be collected for anything other than, we're giving you the legal statement here, right? And it's only for the capstone project. So what's going to happen is I'm going to give you a link, and then you're going to go out and complete the survey. And when you tell it to, submit your answers, there's going to be a screen pop up that says, "Thank you for completing the survey." Look, I don't give a shit what screen pops up when you've submitted your survey. I don't know if it's going to say that or whatever it says. I don't really care what it says. I just want a screenshot of that screen, whatever shows up, all right? And what you're going to do is you're going to take that screenshot and you're going to upload that picture to the Dropbox in DQL, and the Dropbox is titled Class Survey Screenshot. That's how I know that you've done it, right? And so at the end of the semester, I'm going to look at that Dropbox, and everybody that submitted me a picture where you've actually taken the survey is going to get 5 points added to your total. Think about it like this. It's like a question on a test. So there's the deal. And so I've also, they gave me this link here on how to do a screenshot on various incarnations of Windows, Mac, and Chrome OS. Look, if I'm a Mac guy, I'm doing like Shift Command 4. If I'm a PC person, I'm doing a little snipping tool. Those are the only ones I know. Check that out. The link for the survey is under Content Class Survey, and again, it must be completed by 5 o'clock March 8th. So here's where the link is. I'll show you what the thing looks like. It won't show up until 7 o'clock tonight, so if you're looking at it for it now, it's not going to happen. It shows up at 7. So I click that. It opens me up a new window, and it takes me out here to Math 1330 Spring 2019 Survey. All this will remind you about it all being anonymous. We click OK. What's your age in years? What gender do you identify with? What's your race? Something about this adverse childhood experiences little quiz you can take to see. They give you a number. All right. Do you prefer to read textbooks in print or electronic device? How much money would you be willing to pay for a hard copy textbook instead of electronic version? In whole dollars, so we're looking at 20, 10, 5, whatever. Have you ever driven an automobile? You got to go next. That's 7 of them. And then, what's the fastest you've ever driven on the highway or interstate? Tell the truth. See, I like that. I looked at this yesterday, and so 8 is how fast have you ever driven an automobile on the highway or interstate in miles per hour? If you enter 0, you've never driven an automobile. I like the next question that follows. How many wrecks have you been in where you were driving? I think 8 and 9 might go together somehow. Or 10 does. There's 10 questions. So you answer them all. At the bottom, and there's more. Oh, dear God, there's 11, 12. Hell, I quit at 10 yesterday. There's 15, sorry. And then, so at the end there, you click done. I don't want to do it and screw up because, it's collecting everybody's data. Just give everything a blank here. And then whatever screen pops up now, take a screenshot of it. All right? And when you do the screenshot, what I want is, under evaluation, there's a Dropbox. You're just going to upload your picture to that Dropbox, and there'll be one there called Class Survey Screenshot. Right? So you'll upload that. I'll see it. At the end of the semester, I'll add 5 points to your grade. And again, this doesn't open until 7 o'clock. The link's not good until 7 o'clock, and the Dropbox won't show up at 7 o'clock. Now, I'll remind you this I'll remind you that this coming Thursday, next Tuesday, next Thursday, because the next Friday is when we're done with it, okay? So that's what's going to happen with the class survey. We would appreciate it if you would do it. I'm not going to scream at you if you don't. I'm just going to keep reminding you about it. You know, it's 5 free points. There's 15 questions. What are we talking about? 5 minutes? It doesn't seem to be that difficult of a request. Now, we're changing parts of the book. And every time I tell you that, you guys look at me like, what do you mean? Well, you know, I group chapters together, and chapters 8 and 9 go together. So here's the thing. Up until now, I don't care what problem we talked about or what we talked about, a histogram, a stem plot, 5-number summary, somebody always gave me the data, right? The data's always been given to me. Well, what chapters 8 and 9 are about is how do you produce the data? And there's 2 different ways of doing it. In chapter 8, what we're going to learn about is producing data. And the way we're going to produce it here is through sampling. The way we're going to do it in chapter 9 is through experiments. Now, here's the thing. Before I get to writing anything down and all this, is there's right ways to do this and there's wrong ways to do this. And what I mean is this. There's ways to do this, the correct way to do it, right? And what will happen is we can trust what we're learning from the data. And then there's wrong ways to do it that you can't trust what you're learning from the data. All right? So, here's my thought. I'm going to write this question down that the book gives me here, because this is a typical kind of question that statisticians would like to answer. What percent of college students think that people should not obey laws that, the questions are long-winded too, that violate their personal values. Now, here's the other thing about this section. I don't really care what your answer to that question is. I just need something to talk about. You know, if I start talking about the president or this or that, it's just I need something to talk to you about. I'm not here to debate whatever. All right? Now, here's the thing. You see this group we're looking at? There's a whole bunch of college students in the United States, right? I'm talking millions. Are we going to call every one of them? Are we going to contact every one of them? And the answer is no. I still want to answer that kind of question, but there's no way that I can contact every college student. So I'm going to give you this. Cannot ask all college students. Just like if I wanted to ask somebody about some political question, I cannot contact all registered voters, for example. All right? So the way this is going to work is, the question is about this gigantic group of college students. We cannot talk to every college student. We can't get an answer from every one of them on this question. So what we do is, we ask a sample chosen to represent the entire student population. There's 2 words I'm going to underline here. This idea of a sample and this idea of a population. Okay? Now, what this chapter is all about. Okay? How do we choose the sample That's not all of it. There's more to it than just how do we choose the sample. How do we choose the sample so that it is representative of, and I'm just going to say, whatever population we are interested in. So the magic word here, and I'm going to beg for this through most of this chapter, I want a sample that represents our population. In other words, how am I going to go from this large group down to this smaller group? How am I going to go from like a million college students down to, let's say, 500 of them, and have those 500, fairly represent what the population looks like? All right. So here's the thing. I'm on page 206 in your book, and there are 3 definitions here. All right, and they're going to talk about the population, this large group, versus the sample, the small group. Okay? So here's the bottom line. We want info about a large group. Whether you're looking at all college students, all registered voters, whatever it is. My group is just, this large group is just so big that I can't deal with it. And the problem is, I'm not going to write this part down, but we don't have the time, the money, or enough people. It's just not convenient enough to talk to everybody in the large group. All right? So the way it works is like this. We gather the info on only a part. Now, that's not the end of the story. We only gather the info from a part of this large group in order to draw conclusions. So you're going to see my hands move like this. I've got this large group up here, this population, that I want to answer a question about. And what this chapter is going to teach us how to do is how do I go from this large group down to my smaller group called the sample, so that this sample actually represents this population up here. All right? And so then that brings me to these 3 definitions here. And then I'm going to kind of draw you a picture to tell you where we're headed here. It says the population in a statistical study is the entire group of individuals about which we want information. So I think about it like this. The population, we want info. Here. When I say info, it might be I want to know something about the population. I want to answer some question about the population. That's what I mean about info. And then there is the sample. And it says a sample is a part of the population from which we actually collect the information. We use a sample to draw conclusions about the entire population. So here's what I think about the sample. Collect info here. And all our work is done with the sample. Right? That's what we mean by collect the info. In other words, put it this way, whatever the question is I want about this population, I ask that question to my sample. And then I'm going to do all the work with this smaller group about the sample. And then my whole idea is use what I've learned from the sample to draw a conclusion about that population that I had the question about to start with. There's a third one here. Right? So the third one is something called the sampling design. It says the sampling design describes exactly how to choose a sample. So the way I think about the sampling design is how the sample is chosen. There's wrong ways to do this. There's right ways to do this. Now, here's the picture I have in my head when I think about this, right? It's this. Up here sits my population, right? That's my large group. That's where I really want to know everything. So up here's my population. And I'm going to put, there's a question here that I want to answer, like, what percent of college students think that people that shouldn't obey laws that violate their beliefs, right? So there's a question there. The problem is that the population is too large. I don't have enough time. I don't have enough money. I don't have enough people to actually ask everybody in the population. So what do? We come down here to this smaller group, which is the sample. Well, what we do down here is you actually answer the question. Right? Okay, so now we're down to maybe 500 or 1,000 college students, and you actually ask them what they think, and then so you'll get a percentage out of that sample. Okay? So the punchline is this. Before me and you are done this semester, and it's not in this chapter, the chapter we're dealing with is this. How do I get from the population down to this sample? What's the right way to do this? But before we're done with the semester, I want to take what I've learned from my sample, that I've learned in Chapter 8 how to produce this sample so it's representative of the population, and I want to do that little blue arrow, and I want to go back and I want to say something about that question about the population. So you see this blue one here? This is called statistical inference. What that means is to take what you've learned about your sample and infer back to the question about the population. Draw some conclusion about that question you originally had. Now, do you guys think that you see this ever anyway? Here's the thing. I'm going to use political polls. There's always these political polls out here like, okay, so we're looking at, for example, the president's approval rating. Sometimes they flash him up on the TV if you're watching that. Hell, they're on any kind of, like I'm thinking, okay, what's the right devices these days? They'll say, okay, well, they're in the newspaper. I don't even think there is a newspaper anymore. You go look at the news on the internet, right? And there'll be polls there. And I'm always curious about what the poll says because, these days there's probably about, thinking about who our president is, the approval rating is probably about, 30% think he's doing a good job and 70% think he's not doing a good job, right? Did they ask every registered voter when they did that? When they show you these polls, did they talk to every registered voter? The answer is no. If you read the fine print in the poll, they've probably sampled like 1,500 registered voters. So why are they actually showing you the poll if there's millions and millions of registered voters and they're only showing you what 1,500 of them said? That's my little blue arrow there. They're taking what they've learned from their poll of 1,500 and they're trying to infer back about the question about what all registered voters would say. Now, everybody put your shit down for a second and look at me just 1 second. Here's the problem with doing this. Where there's a question about this huge population I want to answer, and I take this small sample and I answer the question here, right? So I do all my work, all my calculations, all my question answering in the sample, and then when I do that little blue and I want to go infer back, am I always right? And the answer is no, sorry. So eventually me and you have to have a little talk about, wait, what's the title of the class? Anybody know? I mean, I know it's Math 1530. What's the actual title of the class? It's probability and statistics, right? Has anybody seen any probability in this class yet? I know. I shouldn't ask you what the title of the class is. I get all kinds of crazy answers when I normally ask that. It's probability. So eventually, after we come back from spring break, me and you are going to have a little talk about probability. Why? Because I'm really concerned about that statistical inference. Okay, these methods we're using, how often are we correct? Now, that's a probability question, right? I just want you to know where we're headed, because this is all going to get tied together at this point from here. Once we learn how to take samples through the rest of the semester, we start tying the little pieces together. Okay? All right. Here's the thing. I will beg of you, that little red arrow there, that when we're done, that my sample represents the population. Obviously, it's going to be smaller. That's the point. But it should have the it should look like, it should smell like, and it should taste like the population. It should have the same kind of makeup, just be smaller, right? So we can actually deal with it. Okay? Now, a couple things here. Just a little warning about some of this. We always want to choose, and the term is a representative. This is like the second time I've written this tonight. And what that means is I want a sample that represents my population. I don't have any better way to say it than to say I want a representative sample. There's a couple of things here that we need to be aware of. And it doesn't seem like that big a deal on the up front, but it kind of is. What population do we want to describe? And here's what I mean by that. You actually want to know what your population is. So here's the thing. I'm going to take this little thought here for example. When I was looking at college students, who do we include? Do we include full-time students? What about part-time students? What about undergraduates? What about graduate students? What are we talking about with college students? Are we talking about all of them? Are you talking about only undergraduates that are full-time? Or are you talking about undergraduates and graduates that are full-time? Are we going to throw the part-time ones in? Why do I care about what population do we want to describe? See that little blue arrow? If you're talking about college students, and you're only looking at undergraduates full-time, when we take a sample from that and we go to infer back, who can we infer back about? Undergraduates that are full-time. If you didn't have any part-time students in there, you can't say shit about them. If you don't have any graduate students there, you can't say anything about them. So it's very important to know what group you're looking at so that when you go back to infer back, that's who you're drawing conclusions about. You don't get to start grouping other people into there. And the second thing is, this may sound worse than the first one, but my second thought is, and it seems like this should be an obvious thing, what do we want to make? In other words, what's the question you want to talk about? What kind of information do you want here? In other words, what we're asking you about is, what's the variable of interest here? Right? What kind of question are we trying to answer? So that we are precise, so that we can draw conclusions about exactly what we want to look at here. Now, the rest of this section, or take it this way, the rest of this chapter is about how we do this the right way and how we do it the wrong way. And I apologize up front, but your book shows you the wrong way to choose a sample to start with. And we always start with how to sample badly. Now I'm going to circle this, because sampling badly is not a good thing. Okay? Now, I've got two of these, and I'm going to give you examples of both of these. One of these is something called a convenience sample. What that means is these are the easiest to reach. A quick example of a convenience sample is if I wanted to, just for the sake of things, let's say I want to sample undergraduate students on the ETSU campus. And I go to the main campus and I stand outside the library and I talk to the first 20 that pass me. That would be a convenience sampling. Why? I'm sampling the easiest to reach, right? The first 20 that come to me, those are who I talk to. Now, do you think that that would be representative of the entire undergraduate population at ETSU? And the answer is, no, probably no way, right? That's not good. We don't like this idea of sampling the easiest to reach. We don't like this idea of a convenience sample. 2, there's something called voluntary response. Yes, it's a voluntary response sample. And what I'm thinking is, I'm going to give you another term, self-selected. So what are we talking about? You know all those ones where you see there's these call-in polls, these phone-in polls, get on the internet and vote for this? Did you select yourself for those? Did you volunteer your response? And the answer is, yeah. Do you think when I would use one of these voluntary response, one of these ones where I let people self-select themselves from the sample, do you actually believe that my sample would be representative of the population that way? No, you know what happens normally with these voluntary responses? What kind of people actually want to voice their opinion? And it's nothing personal. It's the ones that have really strong opinions, right? Doesn't sometimes when you make the phone call, doesn't it cost your ass 50 cents to vote on a phone call? I'm not paying 50 cents to vote for anything. Right? So I must have a really strong opinion here to want to do that. Both of these are, how many times I got to say it? You see something where they sampled very conveniently like that, or you see something where people volunteer to respond or self-selected, these are no-nos. And what I mean is, both of these sampling designs, bad ones, introduce you knew there was a 4-letter word in this class, right? It just wasn't the one you thought. They introduce bias. In other words, these are biased sampling designs. And what does biased mean? Okay, so here's your definition. I'm going to point to you in your textbook. I am on page 208. And it says, bias. A design of a statistical study is biased if it systematically favors certain outcomes. So biased means to systematically favor certain outcome. Well, we don't want to systematically favor anything. Now, all I want is the truth about the population, right? I don't want to sway the group, the answer one way or the other by the way I chose my sample. This is a no-no always. We never want to bias our sample by using a convenient sampling or a voluntary response, self-selecting. All right? So, look, here's my thought. You can take a look at 8.2 about sampling at the mall. That's an example there. Just look, you can just read it and see that that's convenient sampling. I'm a little interested in example 8.3, online polls. In February 2014, the Michigan online news site, MLive, posted an opinion column providing arrest rates for marijuana throughout Michigan and giving reasons why enforcing marijuana laws was not a good use of public resources. A few days later, they ran a story. Now, right, this is an online poll. Any thoughts about what the people was going to vote? The kind of people was going to show up and vote about this marijuana laws and enforcing them? Yeah, I kind of got a feeling myself. It says, take our online poll. Should Michigan legalize marijuana? Of the 9,684 respondents, 7,906 said yes. I'm still concerned about the, nothing personal, I'm still concerned about the 1,190 that said no. And 588 said decriminalize but not legalize. The results would seem to indicate overwhelming support for legalizing marijuana in Michigan. What's the problem here? Where was I at? That voluntary response? Usually people have a strong opinion will volunteer to respond by getting on the internet and voting for whatever it is. Do you actually think if we actually had a nice random representative sample of, let's say, adults in Michigan, we can get the same things? See, here's the thing. You see this little line down here? I'm looking at the last one right there. When something is biased, it means it systematically favors certain outcomes. So which way is this favoring? In other words, when something is biased and it systematically favors certain outcomes, it's either overestimating what the truth is or it's underestimating what the truth is. Right? That's what it means to be biased. So do you think this poll here, is it overestimating what the Michigan residents think or is it underestimating what the Michigan residents think? Damn, it's definitely overestimating, right? So when it's biased, the truth might be, here. The truth might be here, but if you're giving me some self-selected voluntary response, I'm going to overestimate what the truth is, right? So you're on one side of what we're looking for or the other. Yes? So I just want to get that stuck in your head. Your book's not going to tell you about overestimating or underestimating, but if you're going to systematically favor certain outcomes, then you're either going to overestimate or you're going to underestimate. Now, do I need to say it again? We never do these two. Here's what I mean by that. If you see something where it's convenience sampling, voluntary response, self-selected, and somebody's wrote this nice article in the paper, and you're reading through it and they're trying to convince you of something, my suggestion would be wad that piece of paper up and throw it in the garbage. Because it's not worth anything. Right? Why? The results are biased. They're systematically favoring certain outcomes. They're either going to overestimate the truth or they're going to underestimate the truth. So what is our job? Eliminate bias. Well, how are we going to do that? Well, obviously I can't do convenience sampling. Obviously I can't let people select themselves. So somehow I have to select them. We have to select our sample. So, our first attempt, in case you didn't notice, like the math class part of this has went away and talks for the next two chapters. There's nothing to calculate, really. So there's something called simple random sampling. Okay? Very, very simple here is we want to use chance to choose the sample. Seems like a reasonable thing. I'm going to underline that word there. What we want to make sure is we want to give every individual in the population Can I start shorthanding population, please? I want to make sure we give every individual in the population a chance. And I got to be like a little mathematical with you. Non-zero chance of being selected. That's what we want to do. Now, the simplest idea I have for this, it's not realistic, is names and a hat. So this is what I mean by names and a hat. Is I've got my population, and I've got everybody's name in my population. In other words, I got all college students and I got their names. I got them on little strips of paper, and I got myself a big-ass hat. And I put all those names in that hat. And I'm going to draw, let's just say that for the sake of things, I'm going to draw 500 of them. So if I've got, for example, I got 1 million names in my hat, and all the college students I can think about are in there. When I'm going to draw out any one of the names, what's the chance I draw any one of the names in the hat when I draw one at a time? Does everybody understand that's 1 out of 1 million? So what I do is I draw their name. I'm like, okay, you got selected. I'm going to write your name down. I'm going to put your name back in my hat, and I'm going to shake your hat. And I'm going to draw another one. What's the chance that when I draw the next one out, what's that problem? What's that chance? It's 1 out of 1 million. Am I giving every individual in my population a chance of being selected by drawing names out of a hat? And the answer is, yeah, everybody's name's in there. Now, obviously, we're not going to draw names out of a hat. What we're going to do is, we're going to turn the page to 10, And we're going to have our first good sample design. And I'm going to label this as number 1. And it's called a simple random sample. We always shorthand this as an SRS. That's going to be the one me and you work with all semester, right? We want to make sure that we have a simple random sample from our population. Okay? Now, I want to look at the definition here on page 210, because on your next test 2, one of the questions is going to ask you about this definition. Yes, and I'll remind you it's on page 210 when we get ready to take the test. Okay? It says a simple random sample of size n. All right? Anytime me and you are taking any kind of sample, we always use n, and that's lowercase n. That n is your sample size. Now, you know me and you used lowercase n before, right? When we talked about the number of observations or a set of data. That's because the set of data was actually a sample. Sample size is always lowercase n here. It says it consists of n individuals. Obviously, if the sample size is n, it will consist of n individuals. From the population chosen such a way, now here's where I got to get my thought process right, that every set of n individuals has an equal chance to be actually selected. And I'm going to give you, obviously it has n individuals, but every set of n individuals has an equal chance. That's what makes it a simple random sample. So the method you're using gives every set. That's the way the definition is. That's the way a simple random sample is defined. It's not defined as giving anything about any individual in the population. It's where you look at all the samples of size n, whatever your size is. Now, you guys stop writing for a second. Here's my question. Let's do something I can make a little bit of sense of. Let's say I'm going to choose registered voters and we're going to work local. Right? And just for the sake of things, let's say I'm in Washington County and I want to choose 50 registered voters. Okay? And I'm going to use this idea of this method of a simple random sample that I haven't really showed you how to do it yet. We're going to use that method. Is it possible when I do that that all 50 of them are from Johnson City? I was in Washington County. Is that possible? That all 50 of them live in Johnson City? The answer is yeah. Is it possible that all 50 of them are spread out all through Washington County? A simple random sample gives every sample of size 50 the exact same chance as any other sample of size 50. Yes? They all have the exact same chance. Now, I got to throw this out there. This is not to confuse you. My next little line is, but what a simple random sample does for you, not only does it give every set, every collection of n individuals an equal chance, it gives each individual in the population an equal chance. That's not the definition. That's a fact. That's a little note here after. So that's what it does. The definition is looking at n at a time. All right? The point is this. An SRS, simple random sample, does not favor any part of the population. That's what makes it better than a convenient sampling or a voluntary response. We don't favor any part. Does anybody get left out with a simple random sample? The answer is no. Nobody gets left out. Now, how do you actually choose a simple random sample? And I'm going to show you by hand, just to give you a feel for what's going on here. And I'm going to give you, obviously, Minitab would choose any kind of sample that I wanted here, like a simple random sample. But I'm going to show you by hand. And what I've got is this. There's something called random digits. I want to read you a little definition out of the book. It says random digits, and I'm on page 210 here. It says, a table of random digits is a long string of digits 0 through 9. That's the only digits we have, right? Are the digits 0 through 9. There's actually 10 of them. Okay? With these two properties. Each entry in the table is equally likely to be any of the 10 digits 0 through 9. The entries are independent of each other. What does that mean? Any thought? I don't think I've ever used the word independent on you. What does it mean for, okay, I've got this long string of digits 0 through 9, right? What does it mean for this one to be independent of this one? That means they don't know what the hell each other is, right? Whatever one is doesn't tell you what the next one's going to be or what the next one's going to be. That's what it means to be independent. It says, that is, the knowledge of one part gives you no other information. Now, our table of random digits, this idea of random digits, is table, what table we've been using all along? A. Turns out there's a B. Hey, I think I got it. As a, there's B. So, here's the thing. That table is off your formula sheet. You got a table in the back of the book. Table B is right after table A. I don't mean to be a smart ass, but I don't know the page number. Table B comes after table A, right? And what I want you to notice about your table of random digits, a couple things. They're all going to look similar, right, whichever one you have. You notice the first column's a line number. Like they're telling me this is line 101, 102, all the way down to 125. The only reason the line numbers are there is so that I can actually check your answers, right? So if I tell you to start on line 110, we all start on line 110 so that we can get the right answer. Because I'm going to tell you, if I'm trying to do something and I start on 110 and you start on 120, we ain't getting the same answer. Okay? The other thing I notice is, you see how they're groups in group of 5? You know, there's like 5 digits and then there's a gap and there's 5 digits. That's only for ease of reading. It's got nothing else to do with anything. So look, if you take a look at, for example, you take a look at line 102. Right? I'm looking at the second one down here. Line 102 goes 7, 3, 6, 7, 6. In other words, I'm reading line 102 as single digits. What's the chances of any one of those 10 digits showing up anywhere in that line? In other words, I'm asking about what's the probability? Well, there's any one of the 10 digits, the chances are 1 out of 10, yes? So when I read this table, B as single digits, I think about the chance of any one of the digits 0 through 10 showing up as, in other words, they all have the exact same chance. Think about it like this. How did they come up with this table of random digits? They had a hat, they had 10 strips of paper, they had the digits 0 through 10 on there, 0 through 9, and they drew one out. They wrote it down, put it back, sure. Drew another one out, wrote down the number. That's how they made the table of random digits. Now, here's my question to you. Instead of reading line 102 as single digits, can I read them as pairs? In other words, read them as a 2-digit number. In other words, read it as 73, 67, 64, 71, 50. You see how I'm reading it? In other words, I'm reading them 2 at a time now, right? Line 102 would have been 73, 67, 64, 71, 50, 90, 40, 00, 1, 2, 19, 27. I'm reading them as pairs. What's the chance of any of the pairs 00 through 99 showing up anywhere in that line or anywhere in the table? They're all equally likely. 00 through 99, there is 100 pairs. The chance of any pair showing up anywhere in the table right next to each other is 1 out of 100. Well, can I read the table instead of being single digits or pairs of digits, can I read them as triples? In other words, if I start at line 102, I would read 736, 764, 715, 099, 400, 019, 272. Can I read them as triples? And the answer is, yeah. Well, if I read them as triples, what's the chance of any one of the triples, 0, 0, 0 through 999 showing up? One out of 1,000. Can I read them 4 at a time? 5 at a time? 6 at a time? I got a dumb question here. Could I read down a column? I mean, I'm reading across the road. Could I read down a column? It's a table of random digits. I can read it however you want. Right? That's what it means by a table of random digits. Every digit in there is independent of any other digit. It doesn't know what the hell came before it or what's going to come after. It's just like, okay, we generated this random digit between 0 and 9. Now, here's the way we work a simple random sample using this table. So, choosing an SRS by hand. Okay? So, there's 2 things that need to happen here. We need to, 1, assign a numerical label. Can I tell you what that really means? A number to each individual in the population. Right? So I got to assign everybody a number. Now, but there's a catch about this numerical label, about this number. And the catch is each label has the same number of digits. I know that's unnatural. So for the sake of things, let's say I got 500 individuals in my population. And so you know I want to label them 1 through 500, right? But everybody has to have the same number of digits, and I know it's going to take 3 digits to give the person 500. So what do I do about 1? I write 001, 002, 003. That's what I mean. I will add those zeros out in front so that everybody has, if I got to go from 1 to 500, so that everybody has 3 digits in their label. Suppose I've got 5,000 in my population. I know I want to go from 1 to 5,000, but I need everybody to have 4 digits, right? So I would start labeling 0001 and so on. I'll add 0 so that everybody has 4 digits. Then, once we do that, 2, we use table B. And we read the table according to the number of digits our labels. Or if our labels in our step 1 here has 2 digits, we'll read the table as pairs. If it has 3 digits, we'll read them as 3. If it has 4, we'll read them as 4. Whatever we got to do to match the number of digits in our labels from number 1. Now, here's what I'm thinking. I could show you example 8.4, or me and you could turn over here, and we could look at problem 213, on page 213. Let's do one that's not one of the examples here, just so that I can get you a feel for how to do this by hand. It says in 8.6, we can do that one. Okay?
Yeah.
You're planning a report on apartment living in a college town. You decide to select 4 apartment complexes at random for in-depth interviews with residents. Use a simple random sample app or other software or table B. Me and you're going to use table B. So that I can show you that we all get the same answer if we're doing the same thing in table B. To select a simple random sample of 4. So here's what you want. You want an SRS of size right? It's telling me to select 4 out of however many is here. And we're going to use table B. All right? And it's going to tell me where to start. So this line 133, that's the table that's in the back of your book. You know that one that I was just showing you? There's not a line 133 in it, so you're going to have to find table B in the back of the book for this one. I'll fold back there in a moment. Right? I can't go past 125. It was 125, right? So I can't use line 133, so I'll do exactly what the book says, and I'll go to the back of the book. Now here's the thing. You'll notice they've got things in, like, what they got is in columns here, right? And are they in alphabetical order? I don't give a shit. I just need a list of the population, right? And how many's in my population here? I'm going to count the row, the column. 1, 2, 3, 4, 5, 6, 7, 8, 9. It looks to me like there's 27, right? Okay, 27 in the population. Be more precise. 27 individuals in the population. So my population has a size of 27. And we're going to choose 4. Okay? Now, we have to assign labels to these 27 apartment complexes. Well, so they've kind of got it broken up where I've got these columns, right? So the way I would label them is this. I know I want to go from 1 to 27. Did I count those right? Yeah. The way I would label these is, and I'm going to do this so that you'll label them like this too. I would label, right? I know I want to go from 1 to 9, and then I know I want to go right? So I would label the first column, I want to go from 1 to 9, but I know everybody needs to have 2 digits, so I'm going to go 0, 1, 0, 2, all the way down to 0, 9. The next column I need to start at 10, 11, 12, and so on and so forth, and I'm going to go 19 through 20. So that's step 1. I've assigned every individual in my population a label, and every label has the exact same number of digits too, because I know I have 27 total. Do you understand? If I got 27 total, I'm not going to assign labels that have 3 digits. And there's no way in hell I can assign labels that have a single digit and give everybody a unique number. Okay? So, now we're going to go to table B in your back of the book, please. Does it have a page number back there?
698.
Is it 698? Yeah, it's on 698. So in the back of your book, it's page 698. And so what I'm going to do is I'm going to find line 133. And how am I going to read the digits? I'm going to read them as pairs. Why am I reading them as pairs? Because my labels are pairs. So when I go to 133, you going to tell me? Are you good at this? If we screw up, we'll be all screwed up. Put your finger on whatever you got to do. My first one's 45. Yes? 133. 45. You're not talking. You got to talk to me. I can't do both. 133, 45, 74, 74, and then 04, 18, 07, 65, 56. Oh, I'm going to go all the way across the row. 13, 33, 02, 07, 05, 19, thank you, 23, 18, 13, 20, 95, 47. So all I did was I went all the way across row 133 and I read them as pairs, right? And so what we do is we start at the beginning of my list of pairs and I take the ones that I have a label for. Do I have a label of 45? And the answer is no. 74? No. Do I have somebody that has a label of 04? The answer is yeah. Do I have a label of 18? Look, I know the labels are 0, 1 through 27. Do I have a label of 07? Do I have a label of 65? 56? Can I stop? How many was I trying to choose? So I'm going to choose the ones that have a label of 04, 18, 07, and 13. So then we go back to my little, how we labeled them down the columns, and 04 is 1, 2, 3, 4. That is the Bluffs. That's 04. 18 is at the bottom of the second column, and that is Georgetown. That's 18. 07, Brownstone. That's the one that has 07. And then the one that has 13. I think. Right? So the 4 you're going to choose is the Bluff, the Georgetown, the Brownstone, and Dell Lynn. As long as I numbered everything right down the columns and did all that. Seem right? You can check me? It's okay. So here's my question. We were supposed to have 4. I got my 4. How did I do all that? Well, I just redlined 133 as pairs. Right? I got a couple questions for you. Suppose we were doing this, and I got to the end of line 133 and I didn't have my 4 circled in blue. What would I do? You'd go to 134 and start reading in pairs. It gets you quick. Right? There's nothing special about what row you're in. It's just so we all get the same answer. Let me ask you this. Something else that didn't happen here. Suppose I was reading across, right? And let's say I chose 04. And before I got to 4, I saw 04 again. Do I choose 04 twice? No, you only choose it once, ignore it, and keep going. All right? That's the way it's done by me. That's as simple as, like, if you think about it, that's just like drawing the numbers out of a hat. Insane. Right? Everybody's got a chance. I only wanted to do one of those simple random sample ones like that. That's it. Now, if you want to practice on your own, 8.7 is the same idea. But instead of doing apartment complexes, they're doing minority management. And they're going to choose 3 out of however many is there. So you're still going to label 0, 1 through something, because I know I'm going to need pairs of digits. You understand, nobody in your right mind is going to give you like 1,000 individuals and ask you to do this by hand. Something simple where there's 27 or 30 or 20 or something like that, just so that you get a feel for what's going on. Okay? Now, a couple of thoughts about all this. Okay? We always ask the following question. How was the sample chosen? Now, here's the deal. Very rarely when you get outside of this class is anybody going to tell you they did a simple random sample or they did anything. What you're looking for is, that's our magic word. You want to see the word random. You want somebody to tell me we took a random sample. In other words, what I mean is that you trust the results. I'm going to assume at that point that my sample should be representative of the population. I'm going to assume my sample shouldn't be biased by your sampling design because you did something by chance. You did something in a random fashion here. Okay? That's my first thought. My next thought is this. Inference about a population or about the population. So that's the blue arrow. Right? That's taking what you've learned from your samples and refer back about the question you had about your population. So I didn't write it down here, but I'm going to write it here using information from a sample draw conclusion about a population. That's what statistics is all about. Now, I got a couple of things that I would like to say at this point. At this point, most of it's got to be like common sense. One, we would like trustworthy results. No shit. If I can't trust the results, we waste their time. I'd like trustworthy results. 2 and 3 are a little bit of a problem. We are never exactly correct. See that? And you really want to do this and you're never exactly correct? Yep. 3. If I take a different sample, in other words, do all that again by taking a different sample, I will get different results. Obviously, you take a different sample, you're going to get different results. Now here's the thing. These two right here, that's a problem. You're never exactly correct when you want to infer back, and if you give me a different sample, I take a different sample, even if it's a nice random sample, you're going to get a different result. That should be a problem. Not really. Because what's going to happen is the results that we're going to get obey the laws of probability. That saves it. That's the reason probability is the title of the course. It's not just statistics. There's actually probability here we're going to talk about. 4. What saves us is we give a margin of error. Along with the results. I'm just setting you up for later. Me and you're going to have a whole bunch of talk about giving this margin of error along with the results. Because we have to give some kind of margin of error just so that we can be useful. And then I'm going to give you number 5 here. And this is the part that's really of interest to me in this section. In this part of this chapter is, I'm going to give you this one here as common sense. Eventually I will show you why it's true when I can show you the formula, but right now is larger samples, give more accurate results. And I'm going to start this one like this. That's the part I really want you to remember out of this idea of inference, taking something from a sample and then trying to infer, draw conclusions about a population. At the moment, all that other stuff above there, yeah, that's all true. We want trustworthy results. But the big one here is that larger samples get more accurate results. And think about it like this. I can't show you a formula that shows you this is true. But here's the thing. If I get more and more individuals from the population into my sample, won't my sample be more representative of the population? Let me say that again. So my population's up here. My sample's here. The more individuals I can choose from my population to be in my sample, the more representative my sample will be of your population. So I'm going to give you, obviously, the better my results are going to be, right? Because I got more individuals from my population being in there. Hey, what's the best we could ever do? Forget all this sampling stuff. What's that other term? Anybody ever heard the term census? I need to throw that one out there to you. Census. There ain't no sample when you do a census. Here, try to collect info on every individual in the population. No sample. Try to talk to everybody. Does red help if I do it like this? When somebody's talking to you about a census, there is no sample. They have talked to every individual. They've dealt with every individual in the population, no matter how big the population is. The reason I'm making us think about that is because if you're looking at a census, in other words, you've sampled everybody in your population, you've dealt with everybody in your population, there is no inference. Whatever in the hell your answer you're getting, that's the answer about the population because you did a census. Yes? That's what we mean here. No sample, no inference. You're dealing with every individual in the population here. Now, with all that being said, there are other sampling designs. The simple random sample is not the only good one we have. So, I'm going to do a good sampling designs. What do I mean by that? We're not systematically favoring anything. My good sampling design should produce a sample that's representative of my population. 1. Can I just do that to you now and we all agree that that's the simple random sample? That's like drawing names out of the hat. That's like your building block. That's the beginning of all this. Right? Remember, the simple random sample is the one that gives every set of n individuals of the population an equal chance of being selected. It's all about that particular sample size. Now, I want to give you this definition that's not in your textbook, if you don't mind, this general framework. There's something called a probability sample. All the good ones are probability samples. It's not really a design, it's what the term probability sample means. And what a probability sample is, it's a sample that gives every individual in the population a known non-zero chance to be selected. So, a simple random sample, that is a type of probability sample. Because remember, a simple random sample gives every individual population an equal chance. So that's definitely known and non-zero. All right? Every one of the good sampling designs is going to be a probability sample. It's not how you choose it. It's this definition sitting above all the good ones. Right? They give every individual population a known and non-zero chance of being selected, so you're not leaving anybody out. Right? No chunks, no people, you're not leaving anybody out. 2, this is still the good sampling design. I threw that definition in here because all these are probability samples. There's something called a stratified random notice. So here's what a stratified random sample is. As simple as I can make it. All right? Before you start choosing anything, you divide the population into similar groups called I got to throw that strata out there, but you're going to divide the population into similar groups. And then what you do is sample from So you got these groups. Maybe you divided the population up into 2 groups, 3 groups, whatever the hell it is, and you're going to sample within each group. What that means is you're going to choose an SRS in this group, an SRS in this one, and then you're going to combine to form the full sample. Right, so you know you're looking at a stratified random sample as soon as before they start choosing anybody. Their first move is, oh, let's divide the population up into this group, and this group. Now, I can do this to you like 3 or 4 different ways. My first thought is this. Let's say I want to choose registered voters across the state of Tennessee. Fair enough, right? And I want to choose 1,000 of them. Now, the problem with me choosing a simple random sample is the simple random sample gives every collection, every set of 1,000 registered voters, the same chance of being selected as any other 1,000 set, right? So is it possible that when I choose 1,000 registered voters across the state of Tennessee with a simple random sample, that all 1,000 of them are from Kingsport? Any sample size 1,000 has the same chance as any other sample of 1,000, right? So that's possible. So let's make sure that we're going to do better than this. So, there's that limitations with the simple random sample. Let's use the stratify. And let's do this. Rob? You there? Dude, you're supposed to help me. You're supposed to remind me of this every semester. You guys should know. How many counties are in the state of? All right, it's either 67 or it's 95. Rob?
95.
What, Debbie?
95.
I'll take 95.
95.
Florida's got 67. I used to live, I always had these, West Virginia's got 55, how that's where I'm from, it's 95. So let's do this. Let's make sure that when we choose our registered voters, that we're going to choose them from every county in the state. So what will we do? The first move is divide the state up into counties. Well, shit, that's already done for us, right? So then, let's choose 5 registered voters from that county, 5 from that county, 5 from that county, and when I'm done, I'll take all those 5, there's 95 counties, I put them all together, that's a stratified random sample. How do I know? Because what was the first thing you did? You took the 95 counties, you divided the state into registered voters by the counties, and then you chose out of that one, all 95 counties, and you put all those 95 times 5 together to get your sample, whatever size you're looking at. Let me give you something that we can actually draw a picture of. Let's say I'm going to choose ETSU undergraduates. Everybody that's either looking at me or hearing me, you're an ETSU undergraduate. Because if you're not, then you've probably got a problem. If you're a graduate student taking 50 books. So, let's say I'm going to choose, just for the sake of things, let's say I'm going to choose 400 ETSU undergraduates. All right? So if I did a simple random sample of ETSU undergraduates, is it possible that all 400 of them were freshmen? Is it possible all 400 of them were seniors? How do I make sure that I get some from everybody? That's your stratified, right? We would do this. There's your population. Yep. So I divide the ETSU undergraduates up into freshmen, sophomores, juniors, and seniors. And then I would choose an SRS of size, label all the freshmen from 0, 0, 0, whatever the hell it is, and choose 125 of them. 125, 125. Now, obviously, these are all simple random samples. You do each one separately. You do the freshmen by themselves, the sophomores, the juniors, the seniors. And at the end, what do I mean you're going to combine these to form your full sample? Right here it says my sample. That's a stratified random sample. How do I know? Because what was the first move I did? I took my population and I divided them up into simpler groups. Freshmen, sophomore, juniors, and seniors. Look, if you don't like me dividing it up by freshmen, sophomore, juniors, and seniors, can I divide them up by males and females? Put all the males here, all the females. Choose me a simple random sample of 250 of the males, 250 of the females. What am I guaranteed? My sample is going to have 250 males and 250 females. That's stratified. You always know you're looking at stratified when the first move is take your population, start dividing them up into similar groups. All right, what about registered voters across the state? Instead of me using counties, what about if I divided registered voters up by urban, suburbs, and the rural? And then I choose a simple random sample from the urban, simple random sample from the suburbs, and a simple random sample from the rural. You know, maybe 300 out of each, or whatever I got to have, however many you want. Is that a stratified random sample? I keep giving you examples here. You know you're looking at stratified as soon as they take the population, divide them up into your class, males and females, counties, urban, rural, suburbs. You know that's what happened. Now, there's a number 3 here. There's something called a systematic random sample. Oh, we definitely like that word random in our good sampling designs. Now, the problem with the systematic random sample, it's not in your middle of your chapter here, where it shows up, and I'm going to point you to it. It's on page 227, and it's explained to you in problem 8.43. That's for you to go look at. That is not for you to turn into me. I'm going to explain a systematic random sample like this. And I always think about a systematic random sample when I am I'm manufacturing some kind of good. Some kind of good, right? For example, maybe we're, I don't know, what's your favorite food? Potato chips? Pretzels? Twinkies? Ho-hos? Oatmeal cakes? Pick any of those. Now, you know somebody's got a sample to do quality control, right? To make sure whatever it is what it's supposed to be, taste, look, weight. Yeah? Now, you understand, when you're doing a food product like that or something, you can't do a census, can you? All right, I got the oatmeal cakes, and I'm going to sample all of them. What the hell am I going to sell? You got to take a sample, right? You can't do a census. So, one way to do the census is, so the guy that's taking care of the quality control, he comes in the morning, and he's got these little balls on you got a jar and you got balls, right? They're labeled 0, 1 through 20. Or let's say they're labeled 10 through 20. And he picks one out in the morning. And so this morning he picked 12. And so what he's going to do is, as the product comes, he's going to take every 12th one. He'll take the 12th one off, 24, 36, 48, 60, until the end of the day, and that's his sample. Now, I'm going to give you that first number that's chosen here, whether it's 12 or 15, that has to be done randomly, right? The reason I went from 10 to 20 is I didn't want to pick, let's say, every fourth one. That's just too many. So let's say I want to pick somewhere between 10 and 20, right? From 10 and 21, we pull that number out. Maybe tomorrow he picks 15. So he'll pick the 15th one, 30th, 45th, 60, and so on, right? That's a systematic random sample. On Thursday when we come back, the only one of the good ones we talk about that doesn't have the word random in it. There's something called a multi-stage sample. This is the way national samples are done. To me, you're going to hear me describe this to you on Thursday, this is another good sampling design. It uses chance. It just doesn't have the word random in the title. It's a probability sample, and the catch is this. It's a funnel. Right, when you hear me describe it on Thursday, I funnel down to get my sample. So make sure you get your test back. You notice there's a number out of 40 on there. I had already posted your grades in D2L. I had assigned you an early semester progress report because I had to do that before I got a chance to talk to you. I think I explained that in an email. All right. Be careful going to the house. We'll come back on Thursday. We'll talk about this multi-stage. We'll see you.
Hey, Mike.
Yes.
Very briefly, it's and it's enough buffer to let you know. But on the exam week, I'm not going to be here, so there'll be somebody either that you'll get or Dia will get to do your test for you. Just want to give you a little head.
Are we talking about the final?
Yes.
Really?
I'm going to be out of town that week.
Really?
I am. I'm sorry. I just found out last week the exact which week it was, and it's exam week. So more than likely,
No. You know, the thing is that between the number that you have and the number that's streaming, I can fit them all in your room normally and be there with them.
Probably so.
Because there's like 45 computers in that room in Gilbert, so I can do it and do everybody there.
Okay, well, just however you feel. I just wanted to give you a heads up in advance so you knew for sure.
I appreciate that. Yep.
So you figure it out between now and then. Sorry.
No problem.